Okay, Bismillah ar-Rahman ar-Rahim. So today is lecture number 13 of the course Hydraulics, and in today's lecture we will continue our discussion from the previous lecture about dimension analysis. So we will study in detail what is dimension analysis, the different methods. Now, what is dimension and dimensional analysis? So dimensional analysis is a mathematical technique making use of study of dimensions. So this is a mathematical technique where we study about the dimensions of the different physical quantities in any fluid phenomena. And we try to develop the functional relationship between the different variables, dependent and independent variables. So it deals with the dimensions of physical quantities involved in the phenomena. In dimensional analysis, one first predicts the physical parameters that will influence the flow, and then by grouping these parameters in dimensionless combinations, a better understanding of the flow phenomena is made possible. So what we actually do is that the first step in dimension analysis is that we have to predict the physical parameters that will influence the flow. This is the first step. If, for example, we omit an important parameter or you bring unnecessarily parameters which are not important, significant in that problem, so there will be no benefit. Clear? You will not get the required results if you miss out important parameter. So that's why I told you before that dimensional analysis or similitude. So these are conceptual topics. If your concept is not clear, then there are high chances that you will make a mistake. You must have a good understanding of the fluid phenomena. Only then you can apply these methods to achieve the required objectives. So in this dimension analysis, we are developing a functional relationship between the dependent and independent variables. So that's why if you miss an important parameter, so then definitely the results they will not be accurate. When we solve the problems, so in the problem, normally the fluid problem and the different variables, dependent or independent, so that will be given because the purpose is that how you apply the method of dimensional analysis and you solve the problem. But for example, you are a researcher and you want to study or analyze a fluid phenomena that has not been studied before. So you have to identify that what are the physical parameters that will influence the flow. And then by grouping these parameters in dimensionless combinations, a better understanding of the flow phenomena is made possible. So you can see that if it requires a good understanding first, clear? If you miss any important parameter, so then definitely the required results will not be achieved. So this is important, clear? This dimension analysis is particularly helpful in experimental work. As I already explained in the previous lecture, we considered one case, for example, the change in pressure, the pressure drop, you can say, per unit length. So we identified that what are the parameters that are important. And you can see that there were 5 variables or parameters, and using the dimensional analysis we could reduce to 2. So how much the experimental work is simplified? Clear? Because it provides a guide to those things that significantly influence the phenomena. Thus, it indicates the direction in which the experimental work should go. So you can see that in that particular example, you have to conduct large number of experiments to get a functional relationship. But with the help of dimension analysis, with very much less experiments, we can still achieve the same result. So that's why this dimensional analysis, it is very helpful in research work, in experimental work. Clear? This mathematical technique is used in research work for design and conducting model test. So earlier we studied about the similitude or similarity. So in that you learn that how we use the similarity laws which we develop based on Froude number, Reynolds number, and other numbers. So the laws that we develop in the form of, you remember the scale ratios that we use, and then we can transfer the results between the model and the prototype. So in that case, if you remember, the first thing was that you have to identify that in this specific problem, Reynolds number is important or Froude number is important, and then based on that we establish dynamic similarity and we transfer the results between the model and the prototype, or you can say that we can predict the performance of the prototype from the tests conducted on the scaled models. So this dimensional analysis actually will tell you that whether Reynolds number is important in that phenomena or Froude number is important. You see, there you have to use your knowledge to tell that, okay, this is a pipe flow problem. So then for dynamic similarity, Reynolds number needs to be considered. And based on that, the similarity laws we use to transfer the results between the model and the prototype. So if you do dimensional analysis beforehand, actually it will tell you that you should use the dimensional analysis. So that is why you can see here that this is used in research work for design and conducting the model tests. So this is actually a very powerful technique. So let us study, now that we know the importance of this dimensional analysis. You can see here that this is used for design and for conducting the model test. That's why in other fluid mechanics books, first they discuss dimensional analysis, and then in the second part they discuss the similitude. But anyhow, in our textbook, first we discuss similitude and then we discuss dimensional analysis. Clear? Now to start with, what is dimensional analysis, how we do it, what are the methods available? So let us start step by step. First we study about dimensions and units. So what is a dimension? It is a measure of a physical quantity without numerical values. For example, we say length. So length is a dimension. Clear? For example, we say area. Clear? So area is actually length into length. So that is also a dimension, but then we have two types. But the fundamental dimensions that are the length, the mass, the time, and other quantities. So dimension, a measure of a physical quantity without numerical values. You will see the examples. What is a unit? A unit is a way to assign a number to that dimension. For example, you say, okay, length, but how much is the length? Meter, centimeter, inches, feet. So that is the unit. And then we count how many inches? 3 inches, 3 meter, 3 centimeter. So there are primary dimensions. These are also called fundamental or basic dimensions. These are mass, length, time, temperature, electric current, amount of light, and amount of matter. So in fluid mechanics that we have studied so far, fluid mechanics 1 or fluid mechanics 2 or hydraulics course, so mostly we are concerned with variables whose units, you see, these primary dimensions are most of the time involved: the mass, length, and time. But if we study other areas of engineering, clear, whether chemical, mechanical, or electrical, then in that case maybe temperature, electric current, amount of light, these will also be considered, depends on the nature of the problem. But the primary dimensions that we have studied so far for the variables that are encountered in fluid mechanics, mostly we are concerned with this: mass, length, and time. So that's why our main focus will be then in dimensional analysis. We will consider these most of the time, clear? But if we have other nature of problems, because as I said before, that this dimension analysis is not only in fluid mechanics, it is studied wherever we are going to conduct experiments. So it is used for design of experiments. So that's why different areas of engineering and science, they use dimensional analysis. But remember, our main focus, because of the nature of fluid mechanics problems, our main focus will be on these primary dimensions. These are also called as fundamental or basic dimensions. Now, on all non-primary dimensions can be formed by some combination of the 7 primary dimensions. So we can combine 2 or more of these and to make other dimensions, and those are known as non-primary dimensions. We will study in detail. This is an example that a dimension is a measure of a physical quantity without numerical values. For example, you see length. So it is a dimension, clear? While a unit is a way to assign a number to their dimension. For example, length is a dimension, but centimeter is a unit. Meter, centimeter, inches, feet that we are using commonly in different systems. So that is the unit. And then we count. For example, here the length is 3.2 centimeter. So 2 centimeter, 3 centimeter, 5 centimeter, how many centimeters you add up to make that specific length under consideration, clear? So this is dimension and unit. Next we discuss dimensional homogeneity. This is important when we consider dimensional analysis because it provides the basis, the foundation for the methods that we used in dimensional analysis. So the law or principle of dimensional homogeneity, this is important, and this law or principle of dimensional homogeneity, it says that every additive term in an equation must have the same dimensions. For example, we consider the Bernoulli equation. So Bernoulli equation has different forms. This is one of the form that we consider the three forms of energy: the pressure, energy, kinetic energy, potential energy. So we can write down that in different forms. Clear? One of the form is this. Commonly that we have done so far, we write down energy per unit weight. So that's why you have P by gamma, V square by 2G and Z. So we say that these three forms of energy, this remains constant. This is Bernoulli's theorem. When the fluid moves from one point to another point in a fluid flow. So you can see here, and you have studied extensively, we applied this in pipe flow problems, in open channel flow problems. You can see here that these terms, they have the same units, or you can say the same dimension. Let us we talk about the same dimensions. So you see we have this pressure. So pressure is the force per unit area. Now force is equal to mass into acceleration. So we have mass and acceleration is meter per second square. We can write down length by time square, and we have the area. So we have this area, it is length square, length into length. So you can see here these are the dimensions. If we consider the second term, so we have the density, which is the mass density. It is mass per unit volume. We have mass divided volume is length into length into length. The mass divided by length cube. And we have velocity square. So velocity is meter per second, length by time. You take the square. When you simplify this, you get these dimensions. You can see here same as the above. And third, we consider the rho gz term, the third term. This is rho. So rho is mass density, mass by length cube. G is acceleration due to gravity. So again, it has the unit of acceleration, meter per second square. We have length divided by time square, and Z is the distance, elevation. So it is measured in terms of length. So we get these as the dimensions. So you can see here that for all the additive terms, the dimensions are the same. So it means that this law or principle of dimensional homogeneity says that every additive term in an equation must have the same dimensions. Now, what is the advantage of this? Why it is desirable, clear, that we have a dimensional equation that is dimensionally homogeneous. The principle of dimensional homogeneity, you see, the main advantage here is that when an equation is dimensionally homogeneous, then it is independent of the system of units. You can use in any system of units, the shape will not change. You see that Bernoulli equation we can use whether we have problem in SI system of units or in British gravitational system, FPS system. We do not change the shape of the Bernoulli equation. The second advantage is that if we have this dimensional homogeneity, you see that the same equation we apply to a variety of fluid mechanics problems. You see in the pipe flow, we can apply the Bernoulli equation. In the open channel flow, we can apply the Bernoulli equation. You see, that's why it is one of the fundamental equations in fluid mechanics. If we have non-dimensionally homogeneous equation, then what is the problem? Let us first discuss this. The principle of dimensional homogeneity, this is PDH, it says that all the terms in an equation must have the same dimensions. This is desirable. We like the equations that are dimensionally homogeneous. So it was first formalized in 1822 by Baron Joseph Fourier, this principle of dimensional homogeneity, a French mathematician and physicist, now best known for his Fourier series. When we study mathematics, so we come across the topic what is known as Fourier series. You might have studied in the previous semesters in math courses. So this Fourier series, actually this is very important. This Fourier series I will not go into detail, but just to tell you, actually we apply this in periodic functions. When we encounter any function that is periodic, for example, what I mean by periodic is, you see it goes up, then over, then it goes down, then over, then it goes up, then it is like this, clear? Then it goes over, then goes up, and so on. So you can see that this is a periodic function, clear? You can find this, for example, if you remember in water hammer, the pressure variation, clear, as a result. So if you remember, that was kind of this periodic for ideal case, clear? So in case of maybe in electrical engineering, they have periodic functions, clear? They commonly study this Fourier series maybe as a subject. This is so much important. I don't know if you have studied this, but just to give you a very brief introduction, this is not mathematics class. But let's say we have this periodic function and you want to represent this by a mathematical model. So how we do it? So actually we look to the basic functions that, for example, we have this type of function here and so on. So this is, let's say, this point here, these points here. So this can be represented by y is equal to sine x. Y is equal to sine x, sine function, you can say. And we have the cosine function. If we have these points, clear? So the cosine function, it can go like this. So this can be represented by y is equal to cos of x. You can sketch these graphs. This is cos of x. So what Fourier did is that we combine this sine and cosine to mathematically model any periodic function that we encountered in engineering and any problem which involves periodic functions, clear? So a combination of these we can use to mathematically model periodic function that is actually studied in this Fourier series. So this, coming back to our topic, this principle of dimensional homogeneity, this is a valuable tool for checking equation derivations and engineering calculations. We sometimes use non-homogeneous equations such as the Manning equation. We already use extensively in open channel hydraulics, but this is non-homogeneous equation. We already studied that the dimensions are not the same, the left hand side and the right hand side. That's why you see that the Manning's roughness coefficient, it is not a pure number. It has dimensions. So the Manning's equation, this was empirically developed from experiments. You conduct experiment, you fit the data, do the regression analysis, you develop this equation. And because it comes from the experiment, so that's why it is used in the design of open channel. Clear? So the thing is that what is the problem? You can see here that we studied about the Bernoulli equation independent of units and applied to a variety of problem analysis. Pipe flow, open channel flow, you see a variety of problems. When we have non-homogeneous equation, so you see because it fits the data for specific cases. That's why then the Manning equation will be used for a limited number of problems. Clear? So that's why this dimensional homogeneity, this is very important. And the dimensional analysis, the methods that we are going to study, that will be based on this principle of dimensional homogeneity. It's written PDH in your textbook. And what it says that all the terms in an equation must have the same dimensions. When we apply the method in the dimension analysis, you will see that we have to satisfy this. Now, types of dimensions, there are two types of dimensions. We have fundamental dimensions or fundamental quantities. And we have secondary dimensions or derived quantities. Fundamental dimensions, these are basic quantities, as we already discussed. So now we focus more on the fluid mechanics problems. So as I told you before that mostly we will be concerned with the mass, length and time, distance. So we have this MLT system. You see here that we discuss there are 7 primary dimensions, but as I said that in fluid mechanics, the problems that we studied, mostly we are concerned with mass, length and time. That's why we will be most of the time we will be more concerned about these 3. But it doesn't mean that if we have temperature in a problem, electric current, then we have to consider also these primary dimensions. So now that we look to the topic from fluid mechanics point of view, so that's why we say that we have mass, length and time. Similarly, we can also use force, length and time. Either we have this MLT system or we have this FLT system. Because the two are related to each other by the Newton's second law. These two systems, these are connected by Newton's second law through the relationship force is equal to mass into acceleration. So it means you can interconvert these two. Now in the dimension analysis, so because we will be dealing with the dimensions of the physical quantities, variables that are involved, so you have to use either the MLT system or you have to use the FLT system. You will get the same result. So now this is not a question that should I use the MLT system to solve the problem or should I use the FLT system to solve the problem. This is not a question. You use the MLT system or the FLT system, you will get the same result. So next we have these secondary dimensions. So we have the fundamental dimensions are the primary dimensions, and we have the secondary dimensions. These are also known as derived quantities. So these are those quantities which possess one more than one, because if they are one, then it will reduce to the fundamental dimensions. So these are those quantities which possess more than one fundamental dimensions. For example, we have velocity. So velocity is denoted by distance per unit time. You see more than one primary dimension, so it is a secondary dimension or derived quantities. You might have studied this in maybe the physics in the school or college level. So you already know these things. We have acceleration. It is denoted by distance per unit time square. You can see a combination of more than one fundamental dimensions. Similarly, we have density. It is denoted by mass per unit volume. Again, a combination of more than one fundamental dimension. So these are, and so on. So we have these as secondary dimensions or derived quantities. Since velocity, density, and acceleration involve more than one fundamental quantities, so these are called derived quantities. This table is an example because we will analyze the problems, and in the problems as we learn that dimension analysis deal with the dimensions of the physical quantities in any problem. So you must know the dimensions of the different physical quantities characteristics. Clear? So for example, we have length. So you can see that whether you have MLT system or FLT system, L is used. Similarly, you can have for area volume, for kinematic, we have time, velocity, acceleration, discharge. For dynamic, we have mass, force, pressure, energy, power. So if in any analysis, in any problem, these quantities and other than these are involved, you must know their units and their dimensions. Clear? MLT system or FLT system. Because you see here, if you make a mistake here, then you solve a problem, you will never get the required result. So you must know the dimensions, these units and dimensions for these, which we frequently encountered in fluid mechanics. And you have already studied about them in detail in Fluid Mechanics 1, 2, and in this course. Now, we know about the dimensions and the two systems that you can use, either the MLT system or the FLT system. So what are the methods of dimensional analysis? So there are different methods of dimension analysis. As I told you, this dimension analysis is applicable in many areas of science and engineering. So as per your syllabus, we will discuss two methods. Clear? And the basic principle for those methods is dimensional homogeneity, as we discussed, which means the dimensions of each term in an equation on both sides are equal. So the methods that we are going to study, the two methods that are given in your syllabus. So the basic principle will be that dimensional homogeneity that is ensured, because based on this we do the analysis and try to get results. And you should know that what is dimensional homogeneity, which means that the dimensions of each term in an equation on both sides are equal. So such an equation in which dimensions of each term on both sides of equation are same is known as dimensionally homogeneous equation. And as I said, such equations are independent of the system of units. For example, let us consider this equation that you studied maybe extensively in your fluid mechanics 1 course. So this V is equal to square root of 2gh. Now you can see here that the dimensions of the left hand side, we have the velocity, so it is meter per second, length by time. These are the dimensions. When we consider the right hand side, so you can see here we have acceleration due to gravity, length by time square. H is the height or depth, that is L. You take the square root, so we get these units. So you can see here that the dimensions of left hand side are the same as the dimensions of the right hand side. So we say that this equation, this is dimensionally homogeneous equation. Clear? So remember, this is the basic principle on which the methods of dimension analysis are based that we will discuss. So the following two methods of dimensional analysis are generally used. One is the Rayleigh method. So Rayleigh was a physicist and he got the 1904 Nobel Prize in Physics. So he was a physicist, but he developed this method and we are using it in fluid mechanics also. And the second one, which is now more extensively used, that is known as the Buckingham Pi method. So it was developed by Buckingham. Actually, it was developed by several people, but the credit goes to Buckingham, Edgar Buckingham, because he formalized this method in his publication in 1914. So that is why this is known as the Buckingham Pi method. This is uppercase letter pi. This is uppercase letter pi. I will explain why it is known as the pi method. So in our textbook, the uppercase pi is used. This is the uppercase pi. we are commonly using the lowercase pi. This is the lowercase pi. Clear? So in some books, they also used this lowercase pi for the methods of dimension analysis, but in our textbook, it is used the uppercase pi. So we will use the uppercase pi when we analyze the problems using the Buckingham pi method. Clear? And why it is called this pi method? The reason is that Buckingham used an uppercase pi to represent the product of variables in each group. Clear? Because we are saying that in dimensional analysis we reduce the variables into dimensionless groups. So Buckingham said that, okay, this is one dimensionless group or product, let's say it is pi 1. So he said that, okay, let it be pi 1. Whatever the group is, maybe a Reynolds number, any fruit number, you see they are dimensionless number, or any dimensionless quantity which has no units, dimensionless. So he said let it be pi 1. You solve a problem, you get another dimensionless quantity. He said let it be pi 2. Let it be pi 2, and so on. So based on this, this is known as the Buckingham pi method. So we will study both in detail. Now this method actually is extensively used, and I will explain the reasons for that. Commonly you study the fluid mechanics books that we write today. They will explain the Buckingham pi method. We no longer focus on the Rayleigh method. Even though this is a very serviceable method, but it has been superseded by this Buckingham pi method. But we will study both in detail because these are given in your syllabus. And you will see that why we need to shift from the Rayleigh method to the Buckingham pi method. You will see the reason for that. So that's why this method is now superseded by this method. So the modern fluid mechanics books, they mainly focus on the Buckingham pi method when they talk about the dimensional analysis. So let us start with the Rayleigh method. What is this method, and then how we apply this method in the dimension analysis. So the Rayleigh method of dimensional analysis is a conceptual tool used in physics, chemistry, and in engineering. So this form of dimensional analysis expresses a functional relationship of some variables in the form of an exponential equation. So what we have to do is that first you have to identify the parameters. This will not be given, of course, in the problems that we will solve. So the parameters will be given because here the purpose is that how you apply these methods to do the dimensional analysis. But if you are a researcher and you interact with a new fluid phenomena, you have to identify the important parameters before you apply these methods. So that's why I say that this dimensional analysis and similitude, they require good understanding, otherwise you can make mistakes. These are conceptual topics. Clear? This Rayleigh method, so what we do, we will express them in the form of exponential equation, and then we solve and we calculate the values for those exponents. I will explain in detail the procedure and we solve the problem. Rayleigh method is used for determining the expression for a variable which depends upon maximum 3 or 4 variables only. This is now the limitation comes that I explained that why this Rayleigh method, it has been superseded by the Buckingham method. Clear? So this is actually the reason that if in a fluid mechanics problem we have variables maximum 3 or 4, we can solve the problem, but more than that it becomes very difficult. So that's why we have the Buckingham Pi method that can be extended to any number of variables. In case the number of independent variables becomes more than 4, then it is very difficult to find the expression for the dependent variable. So this is actually the limitation. Although it is a very good method, but as the number of variables increase, then it is very difficult to apply this method. As you will see, we will solve a problem. So that's why now we prefer the Buckingham Pi method, and this Rayleigh method, it has been superseded by the Buckingham Pi method. But anyhow, both are given in your syllabus, so we study both in detail. But nowadays, the modern fluid mechanics books, they mostly focus on the Buckingham Pi method. So what is this method? In this method, a functional relationship of some variables is expressed in the form of an exponential equation which must be dimensionally homogeneous. This is what I say. This principle of dimensional homogeneity, PDH, written in your textbook, this is actually the foundation of these methods. Thus, if x is a variable which depends on other variables, the functional equation can be written as like this: dependent and independent variables. So according to this method, the Rayleigh method, what we do is that x is equal to c, where c is a dimensionless constant, no dimensions. And we write down this as x1, x2, x3 up to xn, and we assign some arbitrary exponents, powers. It can be a, b, c, it can be x, y, z. Because these are arbitrary exponents and we have to determine their values. This is how the method works. So it doesn't matter you write down a, b, c, or you write down x, y, z, it doesn't matter. And why we need to write down this c here? Because the reason is that we want to develop a functional relationship between the variables. So because we do not know the exact relationship, when we do the dimensional analysis, the solution is partial only. This is written in your textbook. So that's why we multiply here a dimensionless constant to make the functional relationship more accurate. Later on, I will explain that how we can calculate this C. So that's why we put it here, because we don't know the exact relationship and the dimension analysis cannot provide the direct relationship. The solution is partial only. That's why we need to multiply here a C. And this C must be determined experimentally. Dimension analysis cannot calculate this C for you. This must be determined experimentally. So I will consider some cases that you are familiar with that we studied in maybe fluid mechanics 2 course. So we will apply the dimension analysis. You will then understand that what I explained now, that dimension analysis provide a partial solution, not 100%. But still we see that this is a very powerful tool and it helps in the design of experiments. So this C is a dimensionless constant, and A, B, C, or you can use X, Y, Z. These are arbitrary powers. The values of these exponents are obtained by comparing the powers of the fundamental dimensions on both sides. That's why we have to ensure that the equation is dimensionally homogeneous. Thus, the expression is obtained for the dependent variable. So this is how the method works. We will solve problem that following these steps that we discuss here. how this method of dimension analysis works. So let us take a simple problem. We have very easy problem, start with very easy problem, then we move to more complex problems so that you understand how this method works. So let us find an expression for the discharge in an open channel flow. This is just an example, can be a pipe flow also, you already studied this. When Q depends on area A and velocity V. So you want to find the functional relationship between these three variables, dependent, independent. Now assume that we do not know the functional relationship. Actually, we know the relationship because you already studied that Q is equal to AV. You already know this. Clear? But let us assume that we don't know the relationship between these, and the theory is not sufficient. We are assuming this. The theory is not sufficient to develop this formula. So what is the alternative? So the alternative is that we can use the dimensional analysis to try to develop the functional relationship. And in the dimensional analysis, we are using the Rayleigh method. We are using this Rayleigh method. Let us see that what we get when we follow these steps. This is dimensional analysis. So let us try to solve this very easy problem, then we can jump to complex problems. So what we do is that first we write down a functional relationship between the variables. So we already know that this Q, this is a function of the area A and the velocity V. These two are the important variables. So now, as I said before, that these are conceptual, these topics, dimension analysis and similitude, these are conceptual topics. Why I said this? Because look here, if you want to establish expression for a discharge in open channel flow, if you miss important variable, for example, you miss velocity, do you expect you will get the equation in the end? Or if you bring here another variable that is not important and you do the analysis, what advantage you will get? It will require extra effort but of no benefit. So that's why in order to get the correct results, the first step is that in that fluid mechanics problem you have to identify the important parameters, otherwise you can lose the direction. Here the purpose is to how apply the method, so that's why in the problems the parameters are given. But if you are a researcher and you are studying a new fluid phenomena, these parameters will not be given to you. You have to identify. So the success of the dimension analysis will depend on your understanding of that. If you miss important variables or you bring unimportant variables, so the problems will become complicated for you, of no benefit. So this is very important step. Now we identify that these are the important variables. Now we can proceed to apply the dimensional analysis and see what we get. Clear? So this can be, this equation, the next step is that this will be written as a power equation. What we mean by this, that we will write down this as Q and we will put C here, a dimensionless constant, into area, and we assign arbitrary exponents. Let's say this is A and we have velocity, this is B. You can write down xy, that is not a problem, because we have to calculate the values of these exponents in the end. So this c is a dimensionless constant, as you saw in the previous slide. This is a dimensionless constant. Now next what we have to do is that we studied that you can apply the MLT system or FLT system. You see, mostly we will be dealing with these. Either you use the MLT system, mass, length, time, or you can use the FLT system. You will get the same result. This is for sure. So this is not a question that should I solve the problem using the MLT system or the force, length, time system. You will get the same result. Let us use the MLT system. Let us use the MLT system to deal with the dimensions of these MLT system. So what we have to do is that you have to write down the dimensions of these quantities. For example, we have discharge. So its units are cubic meter per second. You must now know the dimensions. If you make a mistake here, again, you will have problem. So it means that this can be written as L cube divided by time, and we write down like this. We follow the same notations and conventions as per our textbook. Next we have the area A. So you already know that in SI system the units are square meter, so that's why the dimension that can be written as L square. And we have the velocity, so you already know that this is meter per second, so this can be written as L divided by T. So these are now the dimensions. Clear? So what we have to do is that in this equation we will put the dimensions. So what is the discharge? In this equation you need to put the dimensions. So what is the discharge? For that we have L cube divided by L, T. L cube divided by T. And this will be equal to L square area, and we have this as power. Let us use the brackets here. This is power A, so this is power A here. So the square brackets we will use for these dimensions. Now velocity here we will write down in parentheses. Velocity here, this is L by T. Now this is power B. Now, as I said that dimensional homogeneity is the foundation for these methods. So to satisfy dimensional homogeneity, the exponents of each dimension must be identical on both sides. So what I'm saying here is that, for example, I consider for L, so L here is 3. So we write down here 3 on the left hand side, and this must be equal to 2 times A. So this is 2A and plus B. This is the dimensional homogeneity. 2A plus B. Similarly, for time, we do not have M here, we have time for t. So here it is -1, the exponents, because here what is the power? 1. So -1. And this is equal to minus b here. So this is minus b. So now this is equation 1 and this is equation 2. So what we can do is that we can solve these two equations for the two unknown a and b. So b is equal to 1 from here, and then put b is equal to 1 here, get the value of a. So solving for what? For a and b. So b actually you can easily calculate. B is equal to 1 and then put in equation 1. So we get a is also equal to 1. Why? Because you see here b is equal to 1, 3 minus 1 is 2. 2 divided by 2 is 1. So thus Q that was equal to C and this was equal to area A power A. So what is that? 1. From here you see A power A 1 and V power B, so that B is equal to 1. This is A here and this B here. So we get this Q is equal to AV. This is the functional relationship that you get for C equal to 1. Now in this case we already see that C should have a value of 1, and this is what we already know, that discharge is equal to product of flow area into the flow velocity. So you can see here how dimensional analysis it helps us to develop a functional relationship between the variables here. This is the Rayleigh method. You write down the exponential equation, then we put the dimensions, we apply the principle of dimensional homogeneity, that the exponents of each dimension must be identical on both sides, and then we solve these equations to calculate the values of these exponents, and then we put them back in the equation and simplify. Now this C here is equal to 1, but this C will not be equal to 1 in all the problems. This C will have some value. So the question is that from where that value of C will come. So remember, dimensional analysis cannot calculate the value of C. You can use other notation here, but because this capital C is written in our textbook, so we follow textbook. So this value of C must be determined experimentally. Dimension analysis cannot calculate its value. Clear? So that's why we say that dimension analysis provides a partial solution, not a complete solution. But no doubt you will see we solve other problem that it is a very powerful tool. You can see here we get the result. This is not incorrect. This is what we know, the relationship. Let us take another example. This was very simple case. Find an expression for the speed velocity with which a pressure wave travels through a fluid. Use dimensional analysis, use the Rayleigh method with the following parameters. the compressibility EV, the density rho, and the kinematic viscosity nu of the fluid. So again, here the parameters are known. So that's why the first step is to identify the important parameters. So because we are learning how to apply the method, so that's why these parameters are given to us. Now we want to develop a functional relationship between these variables using the dimensional analysis. So we are applying the Rayleigh procedure. So first we write down the expression. So V is equal to, it is a function of these three independent variables. That is the volume modulus of elasticity EV, we have the mass density rho, and we have the kinematic viscosity. Now we want to establish a functional relationship. Let us see that we do not have the theory to derive this formula. Actually, we did this in fluid mechanics too. I derived this formula for you in unsteady flow problem chapter. If you remember, we developed this formula. But let us now use the dimensional analysis that what we get. So we write down this formula. This you have to express as a power equation. This is what the Rayleigh method says. This will be equal to V, that is a function. Here we will write down C. So we write down a dimensionless constant, and this is because we don't know the exact functional relationship. To take care of that, we multiply with C. So this will be equal to, let me not write down the bracket, this will be then equal to EV power A. We have rho power B, and we have kinematic viscosity power D. You can write down ABC, no problem. You can write down XYZ, no problem. So we have this power equation. C is a dimensionless constant, and again we say that use the MLT system. You can solve these problems by using the FLT system. You must get the same result. Use the MLT system. So first we need to write down the dimensions to avoid any mistake. So we already know that velocity, that is equal to length by time. Similarly, we have EV. So you already know that volume modulus of elasticity has the units of pressure. So this is actually force divided by L square. Now you want to write down in MLT system. So this will be then equal to M divided by L into T square, because F is equal to MA. So it will give us these dimensions in MLT system for EV. Then we have the mass density. So that is the M divided by L cube. And we have the kinematic viscosity. So it has the units of L square divided by time. So these are the dimensions. Now we put these dimensions in this equation here, in the power equation. So what we will get, that L by T for the velocity, Now, in this equation for C, we do not write down dimensions because we already studied that this C is a dimensionless constant. So it has no dimensions. That's why we do not write down any units for any dimensions for C. Next, we have EV power. So it is m by LT square. It will be power A. So this will be equal to m divided by L T square. This is power A. Similarly, we have the density, that will be m by L cube power B, and then we have L square divided by T, and this is power D. You can use XYZ. Now, to satisfy dimensional homogeneity, the exponents of each dimension must be identical on both sides. That is why this is written in your textbook, PDH, Principle of Dimensional Homogeneity. This is the basis for these methods. And to satisfy this PDH, it says that the exponents of each dimension must be identical on both sides. Means the left hand side and the right hand side. So for m, what is m here? 0. Now here, what are the this power here? 1. M is 0 here. So no m, it is 0. What is m here? A. What is m here? Plus B. So let's say this is equation 1. Then we have for L, what is L here? 1. What is L here? Minus A. What is L here? Minus 3B. And what is L here? Plus 2D. Let's say this is equation number 2. And for time, we have here minus 1, minus 2A, and here minus D. So now we have 3 equations in terms of 3 unknown. We can solve. So solving, we will get, solving these 3 equations, we will get A is equal to 1 by 2, B is equal to minus 1 by 2, and C is equal to D. This is D here. So D is equal to 0. This is what we will get. So now in the equation, the power equation, we will replace, we see that V is equal to C. Then we have EV, volume modulus of elasticity, power A. So what is A? 1 by 2. Then we have density, power B. What is B? Minus 1 by 2. And then we have kinematic viscosity, power D. What is D? It is 0. Anything power 0 is 1. So we see that V is equal to C, and it can be written as square root of EV divided by rho. This identifies the basic form of the relation. It also determines that the wave speed is not affected by the fluid kinematic viscosity. And if you remember, this was the formula that we developed. So you get the same result using the dimensional analysis. This is how dimensional analysis is a powerful tool. Clear? So let us take a break. Then we will continue with dimensional analysis.